chlorine-36, but get a different twist using plastic materials. So Ines, the floor is yours.
Thank you very much, Stefan, for the invitation to present in this conference and for the introduction as well. So as he said, I'm working in the Belgian Nuclear Research Center. And today I will basically describe the use of plastic scintillator materials to determine chlorine-36 in graphite samples. So first, let me briefly introduce the context of this project. When the nuclear power plant starts the decommissioning phase, is there any problem?
We can hear you and we see the slides.
Normally it's sharing. Well, I will stop it and I will do it again. Can you see them?
Yes, we see them.
Super. So when the decommissioning of the nuclear power plants, there's one of the main issues. It's the big amount of radioactive waste that is created. And this waste need to be disposed in a near surface disposal or deep geological disposal, depending on the activity level concentration. So in order to sort it out, we need to perform a waste characterization. And if we go to the literature, we can see that there are some critical radionuclides already reported that must be determined in order to comply with the legislation in different type of matrices. So from the list of radionuclides, we can find chlorine-36, which is the target of this project. It's an activation product. It's a long-lived radionuclide, which means it will have a long-term effect on the disposal site. It's a beta particle emitter. It has a high mobility in the environment, and we can find it in samples such as graphite with a range level between 4 and 44 becquerels gram. So nowadays, chlorine-36 has been already reported and determined. So first, in case that we have a solid sample, we need to release the chlorine from the solid matrix. For this purpose, acid digestion, alkali fusion, or pyrolysis have been used. And then the next step is to remove interferences from the matrix. And yeah, through the literature, we could find some techniques such as silver chloride precipitation, cation exchange resins, or solid phase extraction using a specific resin, which is the chlorine resin. And then in order to measure chlorine-36, the most common technique is liquid scintillation counting, but as well, tandem ICP-MS has been reported, and in a lesser extent, accelerator mass spectrometry. So then why chlorine-36 is still a topic of interest? First of all, because there's no solid reference material that we can use to validate our procedures. As well, the amount of waste that is created during this separation procedure sometimes is pretty large. The technical and cost demands are sometimes high, like for example, when we need to use accelerator mass spectrometry to quantify chlorine-36. And last but not least, the turnaround times of the radiochemical separation procedures sometimes are pretty long. So our target is to try to develop or optimize a procedure to use plastic scintillator materials to determine chlorine-36. So here on your left, you can see the plastic scintillating microspheres, which are composed by a polymeric solvent together with primary and secondary scintillators, which are the molecules that you can see on the screen. The composition of plastic scintillators is similar to the composition of a liquid scintillation cocktail. And therefore, the role inside the vial for measuring, it's similar, which is, in our case, chlorine-36 will emit a beta particle that will, and then the solvent will be excited, the energy will be transferred to the scintillator, that afterwards will release this energy, and we will detect it with the photomultiplier. So in our project, we tested 3 different types of plastic scintillator materials. The first ones are the plastic scintillating microspheres, or PSM, which the solvent has a linear chain like the styrene. Then we also tested cross-linked plastic scintillating microspheres, or CPSM, where the solvent is a cross-linker, which will add or increase the stability of the microspheres against aggressive media such as sulfuric acid. And then lastly, we also tested a PR resin. In our case, it was the TKTC Sind resin, which is composed by PSMs coated with a selective extractant. In the case of the resin we used, the extractant is an aliquot 336, which is a tertiary amine with chloride ions. So the optimization of the procedure, first we started with the sample combustion. As I mentioned earlier, we are planning to use graphite samples. So we took 0.5 grams of graphite, and then we combusted by using a pyrolyzer. So one of the targets of this project was to know in which form chlorine was released from the pyrolyzer, either chlorine gas Cl2 or HCl. So then we tested two different setups. The first one is the one that you can see on the picture of your right, where we placed a vial containing microspheres. And as you can see, we also connected a trapping solution after this vial to collect the chlorine that was not retained on the microspheres. And in this type of setup, what we were looking for, it was the gas absorption of chlorine gas on the microspheres. So then for the first setup, our idea was directly measure the vial containing the microspheres by liquid scintillation counting. And for this setup, we used two different microspheres, the PSMs, which is the picture you can see above, and the CPSMs, which is the picture you can see below. And then in the second bubbler, we placed a trapping solution, which was 30 milliliters of 6 millimolar sodium carbonate, in order to collect the chlorine that was not retained by the plastic scintillating microspheres. And then the second setup was using a trapping solution to collect the chlorine. And in this case, what we look for is to retain or collect the HCl, so chlorine released as HCl. And for this type of setup, we tested two different approaches. The first one was mixing the trapping solution with a plastic scintillator material, and the second one was loading this trapping solution into a PR resin, as I mentioned earlier, the TKTC Sind. So then at the end, what we will have is different type of vials containing different type of scintillator materials or liquids, depending on the setup and as well the approach. So we will have a vial containing PSMs or CPSMs, another one containing the PR resin, and the third one is basically to check whether chlorine was retained on the microspheres or it was washed out or like not interacting. So at the end, these vials will be placed in a counter called Wallach Quantulus that is used for liquid scintillation counting measurements. So the outcome of all those experiments, as you can see here, prior to the experiments, we measured a sample containing plastic scintillating microspheres spiked with chlorine 36 in order to see the differences that we could observe on the spectra between measuring chlorine 36 with microspheres and measuring chlorine 36 in a solution, adding the liquid scintillation cocktail. So as you can see, the shape of the spectra is similar. However, the purple one, which is the one with the microspheres, it's slightly shifted to the left. And this is because of a phenomena called particle quench that will happen in case that we measure our radionuclide in a solid matrix, which is the case of the microspheres. Then we did a background check in order to investigate the suitable amount of PSMs as well as the needed counting time. We could conclude that 1 grams of PSMs and 120 minutes of counting time was the suitable parameters in order to check the background, in order to have it as low as possible and as well to have a low detection limit. So then the first test was trying to collect the chlorine released from the pyrolyzer with the microspheres. But as you can see, the green and the purple results are the ones that we obtained after collecting the chlorine with PSMs and CPSMs, and the recoveries were 6 and 11%. And then we went to compare this result with the one we would get while collecting the chlorine with a trapping solution. And as you see, we got 80%. So then we could conclude after these experiments that the chemical recoveries were so low when using PSMs and CPSMs as trapping medium. As well, we could measure between the 50 and the 70% of the chlorine in the second bubbler that we added after the first vial containing the microspheres. And this chemical recovery could be also explained because of a memory effect, chlorine-36 memory effect that we reported previously during the pyrolysis step. And then we could conclude as well that only a small amount of the chlorine released from our sample is released as chlorine gas. And this can be confirmed with the publication regarding the gas absorption in plastic scintillator materials, which in the case of the publication, they tested with radon. Then we went to test the second setup, which was using a trapping solution to collect the chlorine. And then the first approach was mixing this solution with plastic scintillator materials. In our case, we did it during 2 minutes, and then we did filtrate the sample in order to be able to measure the microspheres. So as you can see on the graph of your left, the results that we got depending on the different medias were not good at all. We couldn't see any chlorine interacting or retained on the plastic scintillator materials. However, on the last result that I highlighted in blue, we could see that with 4 millimolar sodium hydrogen carbonate, we could get the 40% of the chlorine recovered. So the conclusions at this stage were that plastic scintillator materials without any extractant coated were not having any chlorine retention, and this could confirm our hypothesis that chloride form is not actually interacting with the plastic scintillator materials unless there's an extractant coated on it. And then we hypothesized that the 40% of the chlorine chemical recovery was due to a short interaction time. And therefore, if we mix it during 1 hour, 2 hours instead of 2 minutes, we will get a higher recovery. But overall, the main conclusion here was that the PR resin was the best performing material. So then we went for the second approach, which was loading the trapping solution into a PR resin and then measure the cartridge right afterwards. So first, we needed to know the more compatible media, the loading media to use in order to completely retain our chlorine. And as you can see on the graph, the most promising loading solution was the 4 millimolar sodium hydrogen carbonate. Then we also wanted to understand why the chemical recovery of loading a solution with sodium carbonate was pretty low. And we saw that the extractant works better in pH between acid and slightly alkaline. So this could explain the lower chemical recovery when loading with sodium carbonate instead of sodium hydrogen carbonate, due to the pH in sodium carbonate was between 10, 11, or 12. So then we investigated by using microscopy the effect of the different loading solutions in the microspheres. So prior to those tests, we analyzed a blank in order to have a reference to compare. And then we did measure the different PR resins loaded with different loading solutions. So as you can see, there's a clear degradation effect on the PR resin loaded with 1 molar sulfuric acid. However, we couldn't see any significant differences between the surface loaded with sodium carbonate and the one with sodium hydrogen carbonate. So then we want to see if it was possible to clean the PR resin from the chlorine-36 retained on it. So for this purpose, we added fractions of 7 milliliters, and after each addition, we were measuring the PR resin cartridge in order to see if the activity of chlorine-36 was decreasing. And just to check, we also measured the collected waste in order to see that the decrease of the activity was agreeing with the value of the chlorine measured on the collected waste. So here I place the outcome of all those experiments, whereas you can see we could completely clean the PR resin using two different cleaning medias, the 4 millimolar sodium hydrogen carbonate, and as well we tested 0.1 molar HCl. So the main difference was the volume that we needed to completely clean the PR resin. And then, considering these two different cleaning medias, we went to investigate if it was possible to reuse this PR resin. And then, based on testing with the two different cleaning medias, we saw that in both cases, after reusing the PR resin, the chemical recoveries were decreasing. And in both cases, after the second reuse, we could see that the chemical recovery dropped to 50%. And this could be explained because of the reaction of the extractant with the anions used to clean. In this case, it was chlorides and hydrogen carbonates, this reaction can become irreversible, forming some crystals. So therefore, the number of sites available inside the resin will be lower while adding the solution. As well, we tested the saturation of the resin. And for this experiment, we tested two different activities of chlorine-36. And as well, we wanted to see the difference on the chemical recovery while adding stable chlorine or avoiding to add it. But we could see that the chemical recovery was not affected by the amount of stable chlorine or the chlorine-36 activity spike. And then we went to investigate where actually chlorine was interacting within the PR resin. So we analyzed a microscopy picture of the PR resin loaded with stable chlorine. And then, as you can see, we saw that with the elemental analysis, only chlorine was present on the union between microspheres, which first agrees with our hypothesis that the chlorine was interacting directly with the extractant and not with the plastic scintillator material. And as well, as you can see on the same picture, it's where it looks like the higher amount of extractant is present. And then the last test of the optimization was to see which radiochemical interferences could affect chlorine-36 determination. So as I said earlier, our goal was applying this procedure in graphite samples. So we analyzed tritium and carbon-14 because we did suspect that will be present in our graphite samples. But as well, we added to these experiments iodine because of the similar chemical behavior with compared to chlorine. So we prepared three different solutions with each solution contained each radionuclide. Then we loaded in different PR resins. And then we could see in the spectra that tritium was not retained, so we couldn't see it on that PR resin. Only the 2% of carbon-14 was retained on the PR resin. However, iodine-129 was fully retained on this resin. So the next step was trying to reduce the interferences or remove them from the PR resin. First, we tested some water, and we could see that we could completely clean the resin from carbon-14, but it was not the case for iodine-129. We also went to test other cleaning media, such as sodium carbonate, sodium sulfate, TMAH, or potassium iodide, but it was not possible to remove or wash out the iodine from this resin. So then our idea was to do a sequential separation, taking into account that iodine will be staying on the fair resin, whereas we could wash out, so retain first the chlorine in the fair resin, wash it out, and load it in a second resin. But for this experiment, we first needed to know the breakthrough volume of the resin. And we could determine that it was after 45 milliliters of 4 millimolar sodium hydrogen carbonate where the recovery started going down. So we reached a compromise with this 45 milliliters with a chlorine recovery of 91%. Then we went to analyze if it was possible to apply this sequential separation. We spike a sample with both chlorine-36 and iodine-129. And then, as a first instance, after loading, we could see that both radionuclides were present on the resin on the top, and the second resin, the one on the bottom, it was clean. So then we added the 45 milliliters I mentioned, and then we could see that iodine was completely retained on the first resin, whereas a pure spectra of chlorine-36 was obtained on the second one, with a recovery of 91%. So after the optimization of this procedure, we went to apply it, first of all, in spike graphite samples. So we took 0.5 grams of a blank graphite, we spike it with chlorine-36 and with 1 milligram of stable chlorine. And after the combustion step, we took the trapping solution, which was 30 milliliters of 4 millimolar sodium hydrogen carbonate containing our chlorine. Then we took a subsample for ion chromatography measurements in order to quantify the chemical recovery. And then the rest of the sample was loaded into a PR resin for scintillation counting measurements. So what we saw first, it was reproducible chemical recoveries between the three replicates with an average value of 65%. And then we compared the activity spiked with the activity measured. And as you can see on the graph, the activity measure agreed within the measurement uncertainty with the activity spike. So then the last step was applying this procedure in a real activated graphite sample, in our case from the Belgian reactor 1. So we took 0.1 grams of activated graphite, and one of our targets at this point was to know if the radionuclides that we did study for the interference removal were still present or not, since we did suspect them in a higher activity. So then we analyzed the final spectra of this after loading the trapping solution into the PR resin. And as you can see, there was no evident presence of tritium or carbon-14, and the only peak that we could see on the spectra was due to the presence of chlorine-36. So then we analyzed 2 replicates of the activated graphite. We calculate the chemical recoveries, which were about 74%. And then we also calculated the chlorine-36 massic activity, which was 3.8 becquerels gram. This value was compared with computed values already reported, which were between 4.1 and 8.3 becquerels gram. And then, as you can see, the values agreed within the measurement uncertainty. So then at this point, we wanted to point the analytical parameters that we did consider, such as the turnaround time, which is 7 hours, which means for us less than 1 working day. Then we also calculated the detection limit, which was 20 millibecquerels gram. And then we compared this value with the clearance or exemption levels established by the legislation in order to see if it was possible to apply our procedure in graphite decommissioning samples. And we could confirm that the detection limit was way lower than the clearance or exemption levels. So this procedure could be applied. And as well, one of the relevant things was that the amount of chemicals involved in this procedure was so low, since we only needed a trapping solution, and therefore we also produce less weight. And this agrees with the ISO 14001, which our lab is certified, has this certification. So to conclude, we developed a method to determine chlorine-36 using different plastic scintillator materials. We could apply it in an actual activated graphite sample from the Belgian reactor 1. The big achievements were that we find the most suitable plastic scintillator material to determine chlorine-36, which was the TKTC Syn resin. And then we got comparable detection limits with other previous methods. So the main advantage of these procedures are that we could avoid any mixed waste, since there's no need to mix a liquid radioactive sample with a liquid scintillation cocktail, which is organic. Then the amount of chemicals, as I said, it was really low, since we only needed the trapping solution. The turnaround time is shorter because in this case, we didn't need to do any further elution step. And as well that the gamma and the beta interferences present on our activated graphite sample were not actually affecting the chlorine-36 quantification. So I would like first to thank ENGIE to sponsor the project, Trischem and University of Barcelona to provide us the plastic scintillator materials, and as well all the co-authors of the paper. So I would also like to thank all of you your attention. So if you have any further questions, I will be happy to reply.
Thank you very much for the very nice presentation. Okay, can you hear me now?
Yeah.
Now it's okay.
Okay, if you could try to repeat the question, we'll see if it's okay.
So how would you dispose of the PSMs that are left over? Because obviously you're saying that you could reuse them, but in case you use like hundreds of becks of chlorine-36, how would you dispose of that potentially contaminated PSM? Like, does it go into waste or incineration?
It's kind of echo. I cannot really hear you properly.
Okay, so the question is how to dispose of the PSM after use. They might contain hundreds of becquerels or more of chlorine-36, so they might be contaminated. So how can you dispose of the PSM after having used them?
Yeah, the idea of cleaning the PEER resin is basically to avoid that any organic waste, it's also containing some radioactive material inside. So like it can be treated actually like as a solid, because if there's no radioactivity on it, it's a chemical solid.
Any other questions? Okay. Well, if there are no other questions, again, thank you very much. We move on to the second presentation. That's Maximilian. I think I've seen you already, so I think you're there. Yeah, okay, see you. Yeah,
Yes,
so
hello.
Maximilian Osman from the University of Münster. Now we start with the first of two